Now we'll talk about it. Okay, so we're going to look at Kepler's third law here. This law of Kepler basically equates the orbital period to the orbital distance, or the semi-major axis, if we're thinking about it for an ellipse. And generally speaking, the way this works is that if we have a star, such as our Sun, and a planet, such as our Earth, we know that that planet's going to move in a fairly circular orbit here. Technically speaking, these orbits are ellipticals. They are ellipses, so they're not circular. They're kind of more like an oval shape, so to speak. We're not going to do a full derivation on how this law applies to an elliptical orbit and how the semi-major axis gets tossed into there. If you're looking for that, you're looking more of like a college level astrophysics course. We're going to talk more about just a circular motion, and most of our planets in our solar system kind of follow along this track. So we're going to talk about a circular motion here. It's a lot easier to derive, and you don't have to worry about a lot of the trig stuff. So if we kind of take a look at this Earth going around, we know this Earth is going in its circular motion, or near circular motion, due to an inward acting force. And this is our centripetal force here. And if we think back to what we know about rotation, we know that this centripetal force is going to be ma, but this acceleration is a centripetal acceleration. So this equation really becomes m v squared over r, where this quantity, v squared over r, is the centripetal acceleration. It's the acceleration that a rotating body experiences inward about the axis of rotation. Now, we also know, thanks to work done by Newton, that a force acting between the Earth and the Sun is due to gravity. It's the gravitational force. So what we can actually say is this centripetal force here, mv squared over r, also has to equal g mm, that's m1 and m2, divided by r squared, where that r value is the orbital distance, or the orbital radius, if we pretend these are circular motions. So if we're looking at this here, and we have this equation, specifically the mv squared over r equals gmm over r squared, we can clean this up quite a bit. We see that some r's divide out, and this mass here, this is actually the mass of Earth, and on this side we have the mass of the Sun and the mass of Earth. So the masses of Earth actually go away. The Earth doesn't matter here. So what we quickly see is that our velocity squared is equal to g times the mass of our Sun divided by r. Well, this is nice, I guess. We know how far away an orbiting planet is from its host star if we know the planet's velocity, but I don't have like a radar gun for space. That's kind of a weird thing to get. What we can pretty easily get for space, though, is the period of a planet, or how long it takes to go around before it comes back to that same location. So, that's how long, if here's a star, if we see the planet here, how long does it take for that planet to get back here? That time is the period. And we can see this with telescopes like the Kepler, or soon to be the James Webb Space Telescope, when we look at orbital transits, which is just when we kind of see a blocking of the star behind it. So whenever we see something like that, we can just time it, start the clock, wait a little bit, and then whenever we see that darkness reoccur, we can stop the clock and say, hey, that's an orbital period. That's a time. So how do we get this equation to get this time in it, this period? Well, once again, if we go back to what we know about circular motion, this circle that this is trying to move through here has some circumference, and we know that circumference, or that distance it's moved through, is equal to 2 pi r. That's a traveled distance. We also know that this planet is moving tangentially at some velocity. And if we think back to our very first unit we did, we know that a displacement, a delta x, equals a velocity times time. Therefore, a time equals a displacement divided by a velocity. And in our case here, this circumference is what we're traveling through. That's our would-be displacement. So we can actually say that the period at which it takes for a planet to go around the sun is equal to 2 pi r, where r is that orbital radius, divided by the velocity of the planet. And what that really allows us to do is to say that the velocity equals 2 pi r over the period. Divide and bring that up. So we have this nice equation right here. And with that, we can actually just go ahead and tuck this 2 pi r over t right into that v squared. This is what allows us to bring our period, or the amount of time it takes for the planet to go around its host star, into this third law setup. So if we do this, what we actually have is the quantity 2 pi r over t squared, because that's what v was, equals g times the mass of the sun divided by r. If we go ahead and clean this up a little bit from here, this square has to go into every single term. So this becomes 4 pi squared r squared over t squared equals g times the mass of the sun over r. And if we clean this up a little bit, moving the terms over here on this side to the left and moving the t squared over, what we eventually get is the form of our third law, which is that the period squared equals 4 pi squared r cubed over g times the mass of your sun or whatever object you're orbiting. Technically speaking, if you worked this out for an ellipse, this form takes a very similar approach, but a few things change here. We still have the 4 pi squared, but that r value, the radius so to speak, becomes the semi-major axis A. So if this does work for, you know, a nice oval or an ellipse shape, divided by g, and then this mass here, it's actually the mass of the system. So it's the mass of all the planets and stars in that orbiting domain, or that you care about. For our solar system, we really don't care about anything else other than our sun. It just doesn't really matter because the sun is 99% of the mass of our solar system. Everything else is, you know, very small with respect to it. So even if you added in all those masses, it wouldn't change your answer much. But technically speaking, if you have a large binary star with another star next to it, and those are orbiting, well, they're really orbiting their center of mass here. So we have to think about what the mass of the entire system is because they're similar to each other. So this right here, this is Kepler's third law in a nutshell. Okay, t squared equals 4 pi squared r cubed over gm, or if you're using this for an ellipse, you could do that as well. Okay. Now, a few notes regarding Kepler's third law before we kind of move on from it. It is important to recognize that if you are using, you know, this nice version right here, or the one for the eclipse, whichever one you prefer, your time, your period, is technically measured in seconds. Your radius or semi-major axis is technically measured in meters, and your mass is actually measured in kilograms in this equation. Okay, that's if you would like to use the 4 pi squared r, or a cubed divided by gm. Astronomers actually like to use slightly different units because it makes life easier. They like to use units that are centered on the idea of Earth. And the reason why we do this is it just makes all the numbers just go away flawlessly. So if I once again draw the sun, and then here's Earth out here, we know that it takes 1 year for the Earth to go around the sun. And that's a standard, like that's our standard Earth year. We came up with that. We also know that the distance the sun away is from the Earth is exactly however far away the sun is from the Earth. What? Yeah, that's a weird definition, but that Earth-Sun distance is exactly one Earth-Sun distance. It's like defining itself. So we have a name for that Earth-Sun distance. We call it the astronomical unit. So this is 1 AU, an astronomical unit there. And that's a distance of r, or a if you'd like to think about the ellipse. What we also know is we know how massive the sun is. The sun has mass equal to exactly 1 sun mass? Yeah, the sun is itself. It's exactly itself. Now, this is kind of weird, but all of these numbers here are 1. So what actually happens when you go and use Kepler's law is for your period of a year, you get 1 year squared equals. Well, let's look at our orbital radius, or the semi-major axis. That's 1 AU. So 1 AU cubed divided by, what's the mass of the sun? Well, it's 1 solar mass. If we look at this, this is just 1 equals 1 over 1, which is unity. That's just 1. So what actually happens if you use features like years, astronomical units, and masses of the sun, your Kepler law actually just becomes t squared equals r cubed over m, or if you'd like, a cubed over m, where m is in terms of the sun, r is in terms of AUs, and t is in terms of years. This does mean if you have like a much larger star, you'll have to convert it into the mass of the sun. If you have something like the planet of Jupiter, you'll have to convert its orbital radius into Earth's units of AUs. I believe for Jupiter it's about 5.18. And it does mean that all your numbers will be in years, which, depending on what you're thinking about, may be nice or it might not be. So conversions do have to go into this, but it does make the math a lot easier. You do get to drop out the 4 pi squared over g, which is nice, but other things just become a little bit weird. Okay, so that's kind of Kepler's third law in a nutshell. Does make life easier, and it is, in general, a way we can relate the period, or how long it takes for a star to go around, or a planet to go around its star, to how far away that planet is from its host. And with that, Kepler's law is finished.